Nothing unusual about this scene. A large station, trains arriving and departing. Yet all is not quite as it may seem. For this is one of the intercity trains of the future, and it's about to take us on a special journey. For a short while, it'll become a sort of time machine and take us back through its own evolution to see how it all came about. The designers set out to improve rail travel in every way possible. The new trains were to be more comfortable, faster and more efficient to operate than ever before. And to make sure, they brought in signal and track engineers, drivers and maintenance men, accountants and caterers. In fact, everyone who would have to do with operating the trains. And their demands added up to a set of specifications which were not easy to attain. Not long ago, a rather different bunch of people were aboard. The railway engineers and scientists who conceived and designed the trains, checking the performance of all the equipment at speeds of 130 miles an hour and more. Part of the philosophy which had guided them was to design the whole train as a series of modules, from buffet car trays to the power cars themselves and everything that went into them, so that every part could be quickly replaced to reduce maintenance time and cost. And there she is, the result of a planning and building operation which took diligent note of every specialist view. A unique engineering concept which has now become a reality, compatible with every aspect of passenger train operation. To achieve still greater reliability, tried and proven equipment has been used, but much of it was developed further to increase power or performance. The main engines are a case in point. Based on the success of an earlier engine, many parts have been redesigned to withstand higher engine output. The single crankshaft of the V engine is coupled to the main rotor of the alternator. The diameters of the crank pins and journals have been increased, and the use of disc crank webs now provides a shorter, stiffer crankshaft. The connecting rod assembly has been strengthened, and the new pistons have a simpler ring layout which promises longer life and lower oil consumption. The cylinder liners are of steel, which minimizes weight, and chromium plated to provide the finest running surface. To prevent gas blow-by, as it's called, the cylinder heads are clamped down onto steel sealing rings, which are copper-plated. The fabricated crankcase has been strengthened and at the same time simplified by using steel castings. The water-cooled manifold fits into the V of the engine, and this forms an ideal mounting for the turbocharger. Exhaust gases pass from the cylinder outlets to the turbine inlets through the exhaust manifolds. The water cooling improves reliability and minimizes any fire hazard. The earlier engine had one block-type fuel pump for each bank of cylinders, the 6 injector pipes being of different shapes. The higher power of the new engine called for a higher fueling rate, and this has been achieved by the use of individual and identical pumps for each cylinder. The new pumps and injectors were tested for 10,000 hours before being accepted as satisfactory. The redesigned engine had to be compact and light enough to fit into the limited space, and such compactness can lead to maintenance problems. But ingenious design has achieved a neat balance between all the factors involved. The result of all the development work is the Valenta, a V12 engine which develops 2,250 horsepower. There are 2 of these engines on every train. All components are tested during manufacture, but the real test comes when all the parts are brought together as an engine. Each engine is tested for 15 hours, during which every aspect of its performance is measured. cooling 2,250 horsepower, the water, air and oil which the engine needs takes a lot of doing. It's done by three pieces of equipment which are designed as modules. The main unit cools the cylinders, the water jacket round the engine and the exhaust manifold. Fitted to the engine itself is a cooler for the turbocharger air, and below it the oil cooler. A large variable speed fan powered by the main engine draws air over the 4 aluminium radiators connected to the 2 cooling circuits. All 4 radiators are identical in design and interchangeable. To provide the largest cooling surface, alternate layers of corrugated and flat plates are built like a sandwich into a block. Air passes along one set of corrugations and the coolant along the next. During the manufacturing process, all points of contact become braced together. These are then treated with a resin to avoid corrosion when in use. The 2 cooling circuits work like this. The engine-mounted pump circulates the coolant through the primary circuit to the engine. It returns through a thermostatic bypass before passing to the 2 upper radiators. At the same time, a pump driven from the gearbox passes the coolant through the second circuit, to the turbocharged cooler and oil cooler, and back to the lower radiators. Numerically controlled machines drill the tube plates of the charge cooler. Rectangular fins through which the tubes will be threaded are pressed out of copper strip. These are stacked and aligned to ease the threading of the tubes. The fins and tubes are then bonded together to form the tube stack. Sets of tube stacks are fitted into tube plates, forming the cooler matrix to which water boxes are bolted. These can easily be removed for cleaning without disturbing other equipment. This is the unit which cools the engine oil. The coolant flows through the tubes, whilst the engine oil is guided over them by sets of baffles. A leakage ring provides separate sealing for each fluid, and so avoids any possibility of the water and oil mixing. After leaving the oil cooler, the coolant passes back to the main unit through the lower radiators and on again to the pump to complete the circuit. The 2 systems are independently controlled by thermostat. As a result of ingenious design, there's a common header tank, and this avoids the need for 2 control systems for level and for filling. To reduce weight, the main unit is designed and built with the use of aircraft engine cooling techniques and materials. It fits neatly into place behind the main engine and can be easily disconnected and replaced whenever necessary. Nowadays, it's important to keep passengers at the right temperature too. Air conditioning sells seats, but it also produces correct humidity, avoids drafts and fumes, and helps to keep the carriages clean. That's unlikely to bother anyone, but it will disappear almost at once. To provide such ideal conditions is simple in theory, but tricky in terms of design and production. In practice, fresh air and air from inside the carriage is drawn through air filters, then over the evaporator and heating units, warmed or cooled, and drawn on by the main fan into the carriage at a preset temperature. The thermostat switches in heating or triggers refrigeration, depending on the adjustment in temperature necessary. The units are self-contained and include a compressor, a condenser, an evaporator, a fan, a 24 kilowatt heater, and the electrical control panel, which operates automatically depending on the demands of the thermostat. The cooling system works in the same way as a domestic refrigerator. Gas first flows through the compressor, which raises its temperature. The hot gas passes onto the condenser, where it gives up its heat to air drawn over it by the fan. The gas then condenses to become a low-temperature liquid as it expands in the evaporator. Air is drawn over the evaporator and returns to the coach, cooler and with a lower moisture content. The unit frames are of heavy angle iron and clad in weatherproof paneling, for each coach carries one of these units which slide in under the main frame. The units are completely piped, wired and fully tested in the 2 factories which build for the new train. The electrical controls are carried on 3 insulated panels which fit into the main frame. Fan heaters for the guards compartment are also provided. They're suitably robust to stand up to continual use alongside the main engines, for guards compartments are situated in each power car. Miniature air conditioning units are also fitted to each driving cab. Rapid and effective braking of high-speed trains calls for techniques almost as complex as those which provide the power. Under the driver's brake handle is an electronic control which provides him with 7 different degrees of braking. Behind him, in each power car, is the main electronic control which regulates the air brake pressure to the wheels. Brake demand is carried by coded impulses along 3 wires which run the length of the train. Brakes are applied from both ends of the train simultaneously. There are only 7 electrical and 1 pneumatic connection to each controller. Each controller produces a 7-step digital code proportional to the brake handle position. This is in the form of energization or not of the 3 wires. The main control unit converts the code into air pressures proportional to the 7 positions of the brake handle. This control module is easily replaceable, for it has only 4 pneumatic connections, including exhaust, and 9 electrical connections. The simplicity of the O-ring seals between piping and components and the ease of printed circuitry takes the modular replacement principle a stage further. This system provides a greatly improved control of the brakes while reducing the complexity of pipework and valves necessary with conventional brake systems. These disc brake assemblies, which provide the ultimate stopping power, are subjected to precise and grueling tests on what is probably the most powerful dynamometer rig in Britain. The flywheels are connected to the same shaft as the wheel and disc under test, and represent the speed and mass equivalent of the vehicle to be braked. This machine can simulate a mass up to 32 tons per wheel and up to speeds of 250 kilometers an hour. Sophisticated instruments record the brake test results. Here, the brake is being actuated pneumatically, as it is on the vehicle itself. With very high-powered brakes, in order to avoid the wheels locking and sliding along the rails with damaging results, it's essential to have a wheel slide prevention system. This system is made up of 2 basic units. The control circuit module is located on the axle end, together with an AC generator which provides a signal in proportion to the axle speed, power for the electrical components, and to maintain the battery's charge. This is a generator being calibrated. The control circuit's nerve center carries the differentiating and detecting circuits, which cause a voltage to be applied to the other basic unit, an electropneumatic valve. This valve is rapidly opened and closed, just releasing the brake as soon as the wheel speed deviates from the train speed, then reapplying the brake. Electricity is necessary for many purposes apart from power to drive the train. Heating, lighting, braking and many control systems, quite apart from luxuries like these. It's all provided by two alternators driven by the main engines. This is the complete rotor of the main and auxiliary alternators, which will be coupled to the engine crankshaft. The main rotor carries 12 magnets or pole bricks, each of which is fixed to the hub with steel studs. The other end of these studs are screwed into bars in the magnets. The windings are of copper strip, insulated with braided glass and bonded to the poles. 4 pole bricks are fitted to the rotor of the auxiliary alternator. Next to the alternators are the brushless exciters and the rotating rectifiers. This is one of the main advantages of an alternator over a generator. No brushes are involved, and therefore there's no electrical contact. Since the link is magnetic, mechanical wear and tear is avoided and maintenance reduced accordingly. The stator assembly carries a stator for each alternator and the exciters. The stator windings are of copper strip, insulated with braided glass and polyester enamel. The traction alternator provides an output of 1,468 kilowatts to power the motors which drive the train. The alternators, together with the rectifiers, traction motors and control equipment, represent a complete electrical propulsion package for the train. This is part of the control module being assembled, and alongside the rectifier equipment which converts the alternator output into direct current for the traction motors. There are 4 of these motors on every power car. The traction motors combine strength with relative lightness and are designed for easy maintenance and speedy replacement when necessary. The control equipment protects the train and guides the flow of power from the alternators. These modules contain electronic regulators which control this power. One is the load regulator, another the voltage regulator, and so on. Each plug-in module is easily replaced and interlocks with the rack to ensure correct location. The locking device prevents accidental disconnection due to shock or vibration and doubles as a handle. The neat carriage ceiling and close carpeted floor hides a lot of intricate equipment which adds to the comfort of passengers. Wiring, ducting, cabling and sound-absorbing materials. At the Derby Carriage Works, the body side framing, roof and end framing for the carriages are formed on separate jigs and welded together. The skin panels are then welded onto the framing before all the sections come together to form a carriage. In another shop, the carriage interiors are fitted out with all the equipment which helps to make the railway the most comfortable way of travelling. At the locomotive works at Crewe, building is to a carefully timed schedule. At 14 construction berths, a power car is being assembled, each a little further advanced than the last. Production in the specialist factories all over Britain had to be so planned that a steady flow of components could come together on time to provide one completed power car every week. These are some of the flexible links fitted between gearbox and motor to absorb vertical movements of the axle. These fiberglass cabs are 50 millimeters thick, reinforced and double-skinned, and give the drivers a particularly high level of protection against impact of any sort. And so the great project goes ahead. 27 complete 7-coach trains, including catering cars, in the first order, together with spare power cars or modules to attach if necessary. Now our time machine has caught up again. Like any good train, it's back in the present and on time. The new trains, designed by railway engineers and built in British factories and the workshops of British Rail Engineering, prove once again that Britain is as capable as ever to meet a major engineering challenge and to succeed.